Every day, hundreds of millions of matchsticks are struck across the world. Yet few people ever ask, why is a match exactly this length? Why doesn't the head explode like fireworks? And why doesn't it extinguish the moment it ignites? Inside your pocket lies a remarkably refined mechanical object, where every millimeter has been optimized through centuries of experimentation, thousands of failures, and countless chemical revolutions. A match is not merely a tool for fire, it is a micro-energy system that combines friction physics, thermodynamics, reaction chemistry, and the subtle art of industrial design. The strange truth is that we fail to recognize its brilliance precisely because it works so well. This is the story of an anonymous masterpiece, proof that true perfection is achieved when something functions so seamlessly that we no longer notice it at all. Imagine if a matchstick were round like a toothpick. You would struggle to strike it without slipping. That is why most matches have a square or rectangular cross-section, a shape that appears simple but represents an optimization between grip, friction, and mass production. In factories, match bodies are sliced from aspen wood into thin sheets only a few millimeters thick, then cut at right angles. The flat geometry allows matches to stack efficiently, resist warping during drying, and produce consistent friction during ignition. From a physics perspective, the square cross-section increases contact area and stabilizes the friction threshold, the precise condition needed for the head to ignite at the botter's right moment, neither too early nor too late. This geometry is more than functional. It is an unspoken language of industry. Once a shape becomes standardized, it turns every match, whether produced in Vietnam, Sweden, or Japan, into part of the same global mechanical rhythm. The red, a blue, or black color of a match head is not simply branding, it is chemistry encoded in color. The coating typically contains antimony trisulfide Sb2S3, potassium chlorate, KClO3, and small amounts of organic dyes. Pigments do more than create appearance. They reveal chemical balance. Too pale suggests insufficient fuel. Too dark indicates excess oxidizer and a higher risk of flare. Some dyes also act as moisture barriers, while many manufacturers add ultrafine glass powder to create micro-roughness, increasing friction during striking. Under a microscope, this painted layer resembles a crystalline landscape where each particle is fixed in place to ensure a precise chain reaction. The color of a match head, therefore, is not merely aesthetic, it is a measure of reliability, a fusion of materials, science, and visual design. If the matchstick is the projectile, then the matchbox is the launch platform. The rough striking surface is not just a patch for friction, it is an independent chemical device. This layer contains red phosphorus P4, ground glass powder, and animal-based adhesive. When the match head slides across it, glass particles generate friction, breaking phosphorus bonds, producing heat, and triggering the reaction with chlorate in the match head. Technically, every strike is a two-stage event. Mechanical energy creates heat, and chemical reactions release oxygen. The marvel lies in the strict separation of these components until the final instant, ensuring safe storage. The matchbox is not an accessory. It is half of the system, a forgotten partner that embodies a core design. Philosophy safety emerges from the right distance between dangerous elements. It is no coincidence that matches are made from aspen wood, an unassuming tree with a remarkable microstructure. Aspen fibers contain millions of microscopic capillaries that allow paraffin wax to distribute evenly from base to tip, much like a circulatory network. As the match burns, vaporized wax rises through these channels, feeding a steady flame without external fuel. Aspen also possesses high microelasticity, allowing it to flex during striking without splintering. This ensures smooth, uniform combustion, something pine or bamboo cannot easily achieve. Laboratory comparisons show that aspen produces the most stable burn profile, sustaining a flame for roughly 5 to 7 seconds, just enough to transfer fire to another material. In this sense, aspen can be seen as a naturally intelligent material, discovered by matchmakers centuries before the modern era of advanced material science. In the 21st century, as sustainability becomes a global slogan, the match industry has required surprisingly little reinvention because it was already green long before the trend existed. Modern factories are phasing out heavy metals, replacing antimony with safer organic compounds, using bio-based paraffin, and applying fully biodegradable coatings. Even matchboxes are now produced from recycled, chlorine-free paper, allowing the entire product to decompose within 6 months. If a matchstick were buried in soil and filmed in time-lapse, it would slowly break down like a fallen leaf, leaving only ash and minerals behind. This industry does not chase environmental trends because it reached ecological balance long ago. Nothing excessive, nothing wasted, nothing lasting longer than its purpose. That is the philosophy of the match, a technology designed to disappear once its mission is complete.